Okay, so now equation number 3. Now, and the easiest way to see where equation number 3 comes from is to imagine a position versus time graph. Imagine a velocity versus time graph. And let's say I start off at some initial velocity, and so my velocity is increasing. So I end up at some final velocity. Again, I'm going to start at some time 0 and end at some time t. Okay, so now we talked about how if you have a position versus time graph, the slope gives you the velocity. Now it turns out you can go back the other way too. So if you have a velocity versus time graph and you want to get the total distance traveled from that, what you do is you need to find the area underneath the graph. So we go from here, initial velocity to final velocity. So to find the total distance traveled, we need to find the area under this graph. Now, I don't think you've gotten quite this far in calculus yet, but there's a whole branch of calculus for finding areas under graphs that's called integral calculus. So, but if we assume we have just a simple shape like this, we don't actually need to do integration to do this. We can actually do it the good old-fashioned way. All right, so we basically got two shapes here. We have a rectangle and we have a triangle. So the way to find the area underneath this graph, we find the area of our rectangle plus the area of our triangle. All right, so total distance we traveled, which is going to be x. So let's see, if we look at, first off, let's look at this rectangle. So the height of this rectangle is v initial, and the width of the rectangle is t. So this is the area of the rectangle. Now, to that, we're going to have to add the area of this triangle. So, and if you remember, the area of a triangle is a half times the base times the height. So now the base, well, is just from 0 to t, or t. And the height now is from here to here. Remember, this was v initial, this was v, so the total height is v minus v initial. So this was the area of the triangle. Okay, so now it's just a matter of rearranging a little bit. So I'm going to write this as x is v initial t, and let's see, if I look here, I have v minus v initial. Now, however, if you look back at what I did over here, you'll notice I have this relationship here. So again, let me just multiply both sides by a t, or actually, I already did that. Look at this guy right here. So v minus v initial is the same thing as a times t. Again, assuming acceleration is constant, which we are. So v minus v initial here is the same thing as a times t. So I'm going to have a 1/2 times a t times v minus v initial, which is the same thing as a times t. So I'm going to wind up with x is v initial t plus 1/2 a times t, or t squared, which kinematic equation number 3.